Thank you, Jenny. So today I'm happy to introduce now Dr. Jonathan Weyn, who just obtained his PhD, was it last month?
Yeah, last month. Well, actually 2 months ago.
Oh, that's right. From the University of Washington in atmospheric science on Ensemble data-driven models for meteorological and subseasonal predictions. After a master in atmospheric science at UW and a bachelor in physics from UT Austin. His research covers machine learning weather forecasting, machine learning applied to ensemble forecastings, and predictability of deep convection. So I think a particularly impressive achievement of Jonathan's is that he won the WX Challenge last year and developed a machine learning-based forecasting tool that was entered in this competition, which, for those of you who don't know, is the largest nationwide competition to forecast the weather and changes. It is a paid meteorological competition and was won last year by Jonathan. And this is directly related to the topic of his webinar today that will explore large ensembles of data-driven global weather prediction models. And with that, Jonathan, I will let you take it away.
All right. Thank you very much, Tom, for the introduction. And thank you, Tom and Jenny, for inviting me to speak today. It's a real privilege. So the topic I will be discussing today is using large ensembles of machine learning global weather prediction models for subseasonal forecasting. So this is work that I did for my PhD thesis with my advisor, Dr. DLWP, and also Rich Caruana at Microsoft Research. And before I begin, I would like to acknowledge funding from a grant from the Office of Naval Research and my own funding from National Defense Science and Engineering Graduate Fellowship, as well as computational resources kindly provided by Microsoft Azure through the AI for Earth program for this project. So just to begin with a very broad overview, as we all know, numerical weather prediction has been steadily evolving and has been termed a quote-unquote quiet revolution, as weather forecasting has gradually increased in accuracy, in large part due to vast advances in numerical representation of atmospheric physics, a large network of data collection from satellites, and of course supercomputing power, which enables us to run current state-of-the-art high-resolution NWP models. More recently, ensembles have shifted to making probabilistic weather forecasts have shifted to making probabilistic forecasts using ensembles, since Lorentz demonstrated in the 1960s that deterministic forecasts of the atmosphere have an intrinsic predictability limit and limited skill as a result beyond 10 to 14 days. So, today's major weather forecasting centers now make probabilistic forecasts using ensembles, which are many equally likely realizations of a forecast. So this enables us to quantify forecast uncertainty, such as this example, where higher than normal standard deviation or uncertainty in a forecast occurs in association with the uncertain forecast for Tropical Cyclone Cristobal earlier this year. Now, of course, having more forecasts in the ensemble is better, but it requires a linearly increasing amount of computational power to compute these. So one might argue that the next big revolution in weather prediction might come from machine learning, which, broadly speaking, is using patterns and data to make predictions by learning to minimize errors relative to truth data in a training set. And machine learning is particularly suited for weather because of the increase in big data, novel algorithms such as deep learning, and efficient computing on graphics processing units, or GPUs. And in fact, we have seen an explosion in the application of machine learning to various tasks in numerical weather prediction in recent years. But what if we could actually throw down the gauntlet at machine learning and challenge it to work as an actual global weather prediction model? It turns out this is actually a very highly complex multidimensional learning problem with a lot of variables both in the inputs and outputs. But this is exactly what we did. We developed what I call our deep learning weather prediction, or DLWP model, as a global weather forecasting tool. Now, I will list right here at the beginning some important caveats with this approach. The first is that we focus of basic atmospheric variables, so that's hardly a forecast. Is that in order to train such a model, we use historical graded reanalysis data, which actually relies on data assimilation using state-of-the-art numerical weather prediction models, so it's not entirely model-free. Nevertheless, we were able to build a model using purely machine learning to make global weather forecasts. So I'll show here an animation where in the middle is the verification state of the atmosphere. The colors are the 500 hectopascal geopotential height, and the black contours are the 1000 hectopascal geopotential height. And on the right is a climatological state calculated daily for reference to show that an approximate long-term forecast has this very smooth nature where all of the interesting features that actually happen in the verification, all of the waves and the cyclones, are kind of damped out. Now, if I actually show here on the left, this is the prediction of a long free-running forecast from our DLWP model. And as you can see, it's producing and evolving interesting weather patterns with a lot more variability than a simple climatological forecast. And in addition, you might observe that as we approach here, this is November, as we approach the winter season, that the model is actually correctly developing lower heights near the North Pole. So this is pretty remarkable. So how does DLWP actually work? So we begin with the task of any numerical weather prediction model, which is to take the input state vector representing the atmosphere, which I call here x, at some time t0, represent it with just this sample image, pass it through some sort of algorithm, which then produces a prediction y for the state of the atmosphere at a future time t1. And if we look at historical data, we know what actually happens at t1 in the form of the observed vector x, which enables us to compute an error metric j for the forecast at this time t1, which here we simply use mean squared error or the squared L2 norm. It will be the task of this algorithm then to produce a forecast that minimizes this error function j. Now, our model actually uses a slight variation on this, which is that it actually takes two consecutive input times t-1 and t0, which are fed to the algorithm to produce two consecutive output times t1 and t2, and we found that this multitask learning approach actually produced better forecasts. And we actually take this one step further, and because we know that this forecast state at t1 and t2 will be fed back to the algorithm to predict the next two forecast states, we can actually compute from our observations the loss function at each of these steps in an iterative sequence and combine them into a total loss function, which is then what the model is actually optimized for. So this helps the model perform better for long-term forecasts and remain indefinitely stable, as you saw in the free-running forecast animation just previously. So the data that are used for our model are the ECMWF Era 5 reanalysis at 1 degree resolution and a 6-hourly time step. So we focused, as I said, on a limited set of variables. So there are 6 currently, namely geopotential height at 500 hectopascal and 1000, the thickness between 3 and 700 hectopascals, 850 millibar temperature, and 2 meter temperature as a measurement of what's going on at the surface. And finally, total column water vapor for moisture in the atmosphere. And in addition to these, we prescribe a few auxiliary inputs, top of atmosphere incoming solar radiation, a land sea mask, and topography, which help orient the model to the actual Earth. As in any machine learning problem, we split our data into training, validation, and testing sets using distinct years to avoid having highly correlated neighboring samples in time. And all of the forecast results that I will be showing are averaged over forecasts made twice weekly in the test set 2017 to 2018. And the specific types of algorithms that we use are convolutional neural networks. And these CNNs are ideally suited for quote-unquote images on a grid, in our case, atmospheric data. They can account for local spatial correlations and identify patterns, edges, and shapes, such as tropical cyclones or weather fronts. However, most atmospheric archive on a singular longitude grid, but this results in an image that has very heavy distortion near the poles where things are very stretched out. And as a result, the translational invariance assumed by the convolutional operations no longer holds. So the way we deal with this is to actually approximate the globe as a cubed sphere, where, as you can see on this example, each face of the cube is shown by a red box, resulting in much less distortion on each of the faces, but still enabling us to apply two-dimensional convolutions on each face. So the advantages of the convolutions on the cube sphere is that we can use existing powerful software tools for 2D convolutions. Because they are all in a fixed location, they're aware of the Earth's orientation. And we also added the novel idea of using independent weights on the polar faces, since they have tests with learning very drastically different flow patterns around the poles as opposed to along the equator. There are other proposed methods in machine learning literature for analysis of 360-degree images, but the cube sphere is a natural starting point and has also shown great success in being used as dynamical cores for global weather prediction models such as the FE3. So this schematic shows the actual architecture of our CNN based on the popular UNet architecture. If you're not familiar with architectures of CNNs, then don't worry too much about this slide. The main important reasons for using this architecture is that it enables learning features at multiple spatial scales using downscaling and upsampling operations within the network, and while at the same time allowing high resolution information to pass through. So this is ideally suited for the very multi-scale task of atmospheric prediction. So can we actually improve upon single deterministic DLWP forecasts now by designing a good performing large ensemble prediction system? In the same vein that NWP has evolved to make probabilistic forecasts. So it turns out we can do this because DLWP actually has a significant computational advantage in its current form relative to current atmospheric physical models. So we could ask as a thought experiment how long it would take to run a huge 1,000 member ensemble of 1 month forecasts at 1.5 degree resolution, which is what our model does. The answer is 10 minutes. Not only is it just 10 minutes, but it's 10 minutes on a single workstation with a single GPU. If you take a comparable dynamical model run on a single workstation CPU hardware, this same task would take about 16 days. Now, I will note that the CNNs do require a few days to actually train the model, but this doesn't necessarily factor into the actual cost of making predictions. All right, so the design of the DLWP ensemble now. So we account for both observation uncertainty in the form of initial condition perturbations. For simplicity, although this is suboptimal, we use as initial condition perturbations the perturbed members from the Era 5 reanalysis. And then we also account for model uncertainty using stochastic perturbations, which are actually, in our case, done by training multiple CNNs with different random initialization of weights within the model and shuffling of training data during gradient descent optimization. And you can think of this as being analogous to sort of swapping the physics modules within existing NWP models, such as swapping the convection scheme. Now, each model, I will note, has a mean bias correction applied. So in the interest of time, I won't go through the details of this, but feel free to ask about this later. So here's a chart comparing our current approach with the DLWP ensemble with that of the operational European Center ensemble, which is what I will be comparing to. So in terms of variables, DLWP is far inferior to ECMWF with only 6 two-dimensional variables. And in terms of resolution, we're operating at about 1.5 degrees, whereas ECMWF is all the way down to 18 kilometers in our current ensemble configuration. The other physics that I mentioned are accounted for by those prescribed inputs. Our model also does not have any sort of coupling to ocean wave or sea ice models. However, where we do make up ground versus the ECMWF is in each 32 stochastic CNNs, we have a total ensemble of 320 versus their 50-member ensemble. So let's go right into seeing how our ensemble performs relative to ECMWF and some other benchmarks in the average forecast error in 500 hectopascal geopotential. So here on the left is root mean squared error. So in RMSE, better forecasts have lower error. So this RMSE is a function of forecast lead time. So the blue line here is the control forecast from the DLWP ensemble, where the green solid line is the ensemble mean. And as you can see, the ensemble mean does result in an improvement of performance relative to a single control forecast. But in both of these cases, we lagged the ECMWF operational forecast by about 2 to 3 days of forecast lead time to get to the same amount of root mean squared error. And I will also point out that our ensemble does behave as we would expect in root mean squared error, where the control forecast approaches that of the error in persistence of a random guess of the atmospheric state in the future, which is square root of 2 times the climatological error, which is where we expect the ensemble mean to be in the long term. So this is certainly encouraging. Now, if we also look at the anomaly correlation coefficient, so this measures actual skill relative to a climatological forecast, namely skill in capturing the spatial patterns of where we are, the anomalies relative to climatology. And here you can clearly see that the ensemble mean is providing useful additional skill relative to the single control forecast. Although once again, it's about 3 days behind in terms of equal metrics relative to the ECMWF ensemble. Now, if you also look at 850 hectopascal temperature, the story is essentially the same. So it looks very much the same as the previous plot. Again, about 2 to 3 days, although this difference is actually a little bit less in T850 than it was in Z500. And again, looking at the anomaly correlation skill, we see a very similar pattern. So our model is able to forecast not just Z500, but also thermodynamic variables such as 850 hectopascal temperature. So just to summarize the ensemble prediction system, so we constructed an ensemble of our DLWP models, which accounts for both observation and model uncertainty. Our medium forecast range skill increases with this use of the ensemble, lags the ECMWF, the state-of-the-art ECMWF ensemble by only about 2 to 3 days of forecast lead time. And I didn't show any specific evidence of this, but we have observed that the DLWP tends to struggle with the more dynamically driven synoptic patterns in winter, which is where traditional models excel. But DLWP actually performs pretty well during the summer months. And again, just to reiterate, these forecasts are run extremely efficiently. So 1 week forecast takes about 1/10 of a second for a single ensemble member. So even though our single deterministic forecast skill is deficient relative to the ECMWF ensemble, can we leverage the fact that we have a very large ensemble to produce skillful subseasonal to seasonal or S2S forecasts? And so why might we be particularly interested in the S2S forecast range? Well, so this figure sort of summarizes qualitatively the sense of how good our forecast skill is at various temporal ranges. Obviously, short-term weather forecasts are extremely good before chaos sets and makes things a little bit harder rather than 10 to 14-day range. At the other end of the spectrum, seasonal outlooks, which are like monthly or 3-monthly averaged forecasts, are actually pretty decent, leveraging information about slowly varying components of the air system, such as sea surface temperatures. However, S2S predictions sort of fall in this intermediate range where skill is not where we would like it to be. So some of the particular challenges in S2S forecasting arise from the fact that it is outside the range of predictability coming from initial conditions, but not quite long enough for changes in the slowly varying components like the ocean to provide significant skill versus persistence forecasts. S2S time range is also dominated by intraseasonal climate modes, such as the Madden-Julian oscillation, and is very much regulated by interannual variability such as ENSO. And there's very good evidence that large ensembles are required accurately sample probabilistic forecasts at increasing forecast lead times. All right, so let's just dive right in here and look at some probabilistic skill scores of S2S forecasts from our model as compared to the ECMWF. So the skill metric I will be showing here is the ranked probability skill score. So without putting a bunch of equations on the slide, I will just walk through how this is focused, how this is computed, and how to interpret it. So first, we define 3 equally probable terciles relative to a 1981 to 2010 climatology, which describe when conditions are below, near, or above normal, again, relative to climatology. So the predicted forecast probability is simply the fraction of ensemble members that fall into each of these terciles. We then evaluate a squared error of the forecast probability versus the category that was actually observed, and normalize this squared error relative to a forecast that is just random chance. So a random chance forecast was simply assigned 33% likelihood to each of these categories since they are climatologically equally likely. So the result of this is that a perfect score is 1, a higher score is better, and a negative score means that there is no skill relative to random chance. So the minimum bar to clear is a score greater than 0. So this is the ranked probability skill score in T850 from both ensembles as a function of averaged lead times from 6 to 10 days to week 2, 3, week 4, and then weeks 5 to 6 average. And as you can see, the DLWP ensemble, this is global mean averaged over the entire test set. On the average, the DLWP ensemble provides decent positive skill, meaning that it is useful relative to simple climatology forecasts, although it is not quite up to where the ECMWF ensemble is at the moment. I will note that this bump in skill in the 5 to 6 weeks is largely affected by the fact that there's a longer time averaging window. If we, instead of looking at the global mean, look at just points that are over land, the difference between the two ensembles is actually reduced to the point that at weeks 5 to 6, the 95% confidence bounds actually overlap. So this is certainly encouraging, but it's also informative to look at maps of where the models have more or less skill. So again, this is annual mean, T850 ranked probability skill score. This is for week 3 forecast, where our DLWP model is on top and the ECMWF ensemble is on the bottom. And the first thing you probably notice is that the majority of the high skill scores occur over the tropics, especially over the oceans. This is not too surprising, as there is a lot of longer-term predictability in the tropics. However, even at week 3, we do see that our DLWP ensemble has positive skill scores over most of the land masses, with exceptions in North America, but is still lagging behind the ECMWF ensemble. If we move on to week 4, both of the ensembles degrade a little bit in quality, unsurprisingly. And ECMWF now has some regions of negative skill over land masses, but is still better than DLWP is. If we go all the way out to weeks 5 to 6, we actually see that the difference between the two models is less. Encouragingly, DLWP still has positive skill scores over nearly all of the land masses, again, with exceptions of parts of North America, but does perform very well in the southern and western North America, over most of the Eurasian, African, and South American continents, and Australia as well. And it looks, in fact, very similar to the positive skill score of the ECMWF ensemble. If we just look at the season where our DLWP model performs best, this is March, April, May. So here on the global average, essentially the score is the same between DLWP and the ECMWF at weeks 5 to 6. we see high positive skill scores, especially over the Western United States and most of the other landmasses. Now, if we look at 2-meter temperature, things are less optimistic here for our DLWP model in the comparison versus ECMWF. ECMWF has very high average skill scores across the different time ranges, but you'll notice that most of the really good score comes from the tropical oceans. If we look at DLWP, it doesn't perform as well over the tropical oceans, which is not surprising because it doesn't have any sort of coupled ocean models included in it so far. But by weeks 5 to 6, we still do see generally positive skill scores, especially over land masses, which is ultimately what we would care most about. And so I mentioned the fact that we don't have an ocean model, and this is really evident if you look right along the equator in the Eastern Pacific. In 2017, I believe, there was an onset of an El Nino event, which was not very well captured by our model, which does not include a coupled ocean, whereas the ECMWF model with its coupled ocean does not have this problem. So I just want to give a little bit of direction for where DLWP might go in the future. Of course, we'd like to further improve the model by adding more variables, further tuning the machine learning algorithms, and also potentially add ocean sea surface temperature data to the model to improve its ENSO and MJO forecasts. Our model currently does not predict precipitation, which is very important for S2S forecasting, especially in terms of forecasting the onset of drought. As I showed in the example animation before, the prediction from DLWP was a little bit smooth relative to verification, so we'd like to focus on improving prediction of extreme events. But then finally, the computational efficiency of DLWP could be leveraged to do idealized case studies or as an adjoint model to study atmospheric predictability. So finally, a couple of summarizing takeaways from this talk. Our purely data-driven algorithms using CNNs can produce realistic and definitely stable global weather forecasts with skill that are behind the ECMWF by about 2 to 3 days of forecast lead time. By using both initial condition perturbations and the internal stochastic randomness of CNNs in the training process, we can produce a good performing data-driven ensemble that requires a lot less computation power than equivalent resolution dynamical models. For weekly average forecast in the S2S forecast range, which is where traditional models struggle, our model has shown to have useful skill relative to climatology and persistence, although still lacking the state of the art in the ECMWF. However, our model performs particularly well in the boreal spring and summer months and in the extratropics and over land, all points where the ECMWF model is weaker than on the global average. So with that, I'm happy to move on to the question phase. Thanks.
Thank you, Jonathan. Reminder, if you have a question, feel free to use the raise your hand button and I'll call on you so you can unmute yourself, or you can type your question into the chat box. Any questions for Jonathan? Okay, I see one from Ime. Go ahead and unmute yourself.
Hi there. Very impressive work, and you know what I think of your work anyway. Since we met before, what are the drawbacks? Just because it's so overwhelming how much it can do and how much faster it is, and just if you look at it, what are the negative parts about using deep learning here?
Well, I think one of the important negatives is it's a little bit difficult necessarily to understand what the model is doing at times. We haven't really researched that yet. So if there are, say a significant bust in the forecast, it might be a little bit difficult to understand why that is going on. of course, we also, can't match all of the potential outputs from, a state-of-the-art NWP model right now. Notably, things like precipitation are still missing, and it's not clear whether, the performance of the model will degrade when we try to add information such as that. So I think this is really, still in its infancy, and I think some of the early results are promising, but it's certainly going to require more work before it's ready to be operationalized or something like that. Yeah.
Thank you.
Any other questions for Jonathan?
I have one.
Yep, go ahead.
This is Amy. Jonathan, that was a very nice talk and very encouraging work. Very nice work.
Thank you.
You're a good explainer. I just had a couple questions. The first one was, you're using root mean squared error as a metric for performance. Does that average over all spatial locations and all times? Is that how you compute that?
Yes, it is.
Yeah.
Yes.
So that could certainly be hiding the fact that in some places it does much better than others, as you have found out by the latter part of your talk.
Yes, of course.
I wonder if you might consider using some other metric besides root mean squared error in order to try to make that more automated. Just a stray thought. Another sort of question / comment is that along the same lines, is root mean squared error pushes together both bias and variance into one number. And I suppose it's possible that some people might be more interested in bias and some people might be more interested in variance, or you might be interested in bias in some places and variances in other places. And so I just wonder if you've considered splitting that root mean squared error into those two parts and keeping track of them separately.
Yes, we have certainly considered doing some of that. It's certainly true that some amount of the error comes from a sort of correctable bias. So I did mention that we were correcting the average model drift in some of these forecasts. And if you look at, so this is actually the average bias of the model relative to verification as we go from week 2 to week 3, week 4, and then weeks 5 to 6. So yeah, there's certainly some interesting things to be determined from there that could, ultimately, I hope be used to figure out where we need to target to improve the model further. And yeah, it's certainly right that some of these global average metrics don't tell the whole story. Yeah.
I see some questions in the chat. So Chidong Zhang, he asks, what selection of input variables part of the DLWP?
Wait, was that which variables are part of it, or what? How did the selection process work? I'm not sure if I got all of that.
So the question was selection of input variables part of the DLWP?
Okay, so I'm going to assume that means how we selected the variables. Yeah, so for sure we wanted to start with something simple. So actually our first work along these lines just had 500 millibar heights. So we were just seeing that whether we could reproduce the simplest dynamical models of the atmosphere. And then we sort of progressively added variables as we went along, in part based on, adding thickness was based on a physical notion that it should help the model learn the growth and decay of storm systems. But then also adding variables that are impacts based and that we care about, like 2-meter temperature. And then, adding total column water vapor was informed by the fact that, the model didn't have any direct information about moisture up until that point. So we certainly made sure that whatever we added, we were not degrading the performance in time, and some required a little bit of an adjustment to the model architecture. But for the most part, gradually adding things has steadily improved the model.
And a question from Andrew Robertson. Does the S2S prediction use the same time step as for weather? How to interpret that physically?
Yes, so the S2S prediction is, well, so our DLWP model is essentially working just like a numerical weather prediction model. So it's integrated forward in time, in our case, in steps of, at a resolution of 6 hours. So to compute the seasonal forecasts, we simply run the forecast out to 6 weeks, and then for the weekly averages, just take the weekly average of the forecast over that period. So the model is run in exactly the same way. It's not specifically targeted for those period of time, which sort of gives us an advantage over machine learning approaches to S2S forecasting, which were very highly targeted and much less flexible at predicting, over long periods or flexible ranges of times or over the whole globe.
A question from Zane Martin. He says, I'm impressed you were able to produce such stable predictions. Can you go into the details more of how this was achieved?
Yeah, so I've heard this question a lot, so it's a very good question. Unfortunately, I don't have the best answer because it's a little bit hard to tease out which of the aspects of our model development contributed more or less, but the end result is that it's a combination of the fact that the first thing is that unlike other approaches to this model emulation, we used the cubed sphere, which enables completely closed boundary conditions. So all of the boundary conditions are correct. So there's no leakage around the boundaries in that sense. The second reason is the minimization of the loss function over a sequence. So basically, this ensured that the model was actually trained to perform well over multiple iterations forward, and therefore we were optimizing its weights to ensure that it would produce realistic things even further out in time and for the process of actually making a forecast. So I think largely it's a combination of those two factors.
Question from Ganzang. The skill over some land regions, for example, North America, seems less good. Is it because land conditions there are inherently harder to predict, or CNNs just picked up some biases from the training data set?
So there certainly is a pronounced warm bias in our model over land masses in the northern hemisphere. To some extent, I think this particular model is struggling a little bit there. We've also sort of observed it not doing quite as well at developing strong storm systems in the northern extratropics. So I think that's part of the deficiency there, but I haven't specifically analyzed why the predictive skill is less good over the northern North America, but this is actually a problem that's present in the ECMWF as well. So these were the T2 rank probability skill scores. So you can see the ECMWF struggles a little bit there. So there might be something more interesting going on there. I'm not exactly sure what that is, but maybe somebody else here does know.
I think this might be a follow-up question from Chidong again. Is there a way to select the best input variables using machine learning?
I'm sure there is. We haven't done those sorts of comprehensive experiments, in part because the problem is that a selected architecture for the neural network is not guaranteed to be in any way optimal when the variables, but it's, I mean, it's certainly possible to set up a sort of experiment with data denial or something like that to see how much each variable contributes and whether certain variables are more useful than others and should be kept or removed.
And then I think a final question before we might open it back up to, I see some people might have other questions, but Paul Ulrich writes in the chat, there were a couple regions in Africa where your model scale was nearly 1 even for the long-term forecasts, and ECMWF had nearly 0 skill. Is that a statistical anomaly or a real result?
Yeah, I haven't looked specifically at those yet. It's certainly true that there's a couple of areas here that might be associated with some topography where the model does really well. I mean, it could be that the simple correction of the model bias enables it to represent do a good job of capturing the typical conditions there. I'm not exactly sure how best to answer that without, we haven't really looked at it further. But yeah.
2 minutes left in this open session. Does anyone else have a question? If not, I can have Mike Pritchard ask a question. All right, I don't see anything. So Mike, did you want to ask probably your most burning question for the public?
Sure, yeah. How scalable is this? It seems it's super provocative. It seems like you would crave, a nice national infrastructure to play with GPU resources at a large enough scale that you could really add lots of input vectors, and I guess that would be entangled with automating some hyperparameter tuning process. But what's the outlook there? Where do you feel limited? Where do you feel like the infrastructure is behind what you would like to daydream about with this?
Yeah, no, great question. I would really like to see more development on this. I think most of the so honestly, I think the biggest bottleneck in this is actually data I/O. Simply loading a lot of data to be fed back and forth between disk, memory, CPU, GPU is really challenging, and I don't have the technical expertise to figure out the best way to do that. But for sure, if there could be some collaboration with technical experts who can improve the data I/O pipeline for something like this, it might be pretty promising. The problem is, ideally we'd like to go to higher resolution, add more variables, etc. But all of these changes really take a big toll, actually, in just in the data loading phase and shuffling data around. Not so much, actually, as it turns out, on the computation phase. The computation is actually quite efficient in comparison. So I think that's where I'd like to see the most improvement.
All right. I think that'll wrap up this open session. So we'll transition into the closed working group only discussion now. So thank you everyone for joining us today. And thank you, Jonathan, for presenting. If you want me to put you in touch with Jonathan, you can send me an email and I can do that. Our next talk is on August 17th, and our presenter is Matthias Katzfuss with the Texas A&M University. His talk title is Scalable Covariance Approximations for Environmental and Climate Data. So hopefully I will see you in a couple weeks then. Thank you everyone for joining.